We call our model the Active Latent Space Shape Model. This is a collaborative work between the departments of Computer Science, Mathematical Science, and Pharmacy and Pharmacology of the University of Bath. We've been working with the National Health Service in trying to automate damage detection in psoriatic arthritis X-rays. There are three main contributions that I go over in this presentation. The first one is the way we align our landmarks. The second one is the statistical shape model that we use, and the third one is how we hybridize a statistical shape model and a discriminator network. Let us first go over the shape model that we use and the training data used to train that shape model. The training data takes the form of landmarks placed around bone outlines. We adopt a continuous parametric representation for these bone outlines, and this allows us to align landmarks that we sample from this parametric representation based on their curvature. The shape model that we use is a Gaussian process latent variable model. What you can see here in this diagram is the posterior mean of the GPLVM sampled at the corresponding latent space position. Using a GPLVM induces a likelihood on the shape that we observe, but it also allows us to induce a nonlinear mapping from the latent space to the shape space. The nonlinear mapping is determined by the choice of kernel that we use. Shape model adaptation usually requires us to evolve the shape onto some potential function, and the potential function should be minimum at locations that are likely to be edges and maximum at locations that are unlikely to be edges. This is why we chose to use a U-net discriminator to build this potential function. Bringing all this together, we have the following graphical network where the GPLVM is generating shape which is warped by some similarity transform onto the image template. The U-net discriminator then measures whether the warp shape is actually at the correct location. From this graphical network, we want to perform the full Bayesian marginalization of the model parameters, which in this case are the generated shape and the warp shape. Once we perform this marginalization, we are left with an objective function consisting of the pose parameters and the shape parameters. We denote the shape parameters here by small t and the pose parameters by curly t. These completely determine the shape that appears in the image, and we want to optimize this objective function with respect to these two parameters. Thank you for watching this video. I hope you enjoyed it. If you have any questions, please do not hesitate to ask me at the question and answer session.